Welcome you all in this lecture. So today's lecture is particle in one-dimensional box. So particle in one-dimensional box, this is, as you know, is an application of Schrödinger wave equation. So here we will discuss how does a particles is behaves in one-dimensional box and what type of relationship in case of the energy, how we can find out the energy of a particle in one-dimensional box. So here, you know, a particle in a box provide us the application of Schrödinger wave equation to the translational motion for particle in an electron atom or electron or small particles. It also explains to why the energies associated are quantized. So the motion of the particle in one-dimensional box is like the flow of an electron in a wire, but still is called particle in box. And a general case can be considered in which we may assume that a single particle like a gas molecule of mass having m is restricted to move in a region of the space x equal to 0 to x equal to a. So this is the space from where these particles can move, and it is a potential, and its potential energy within the box is considered and taken as equal to 0 for the sake of convenience. So here you can see like in a particle in a one-dimensional box. So inside the box the potential energy is constant to all, so this is taken as 0. At outside the box this will be taken as infinite. So like x equal to 0, so x equal to a, within this space the electron is restricted. So particle is one dimensional box. As we already said, potential energy inside the box will be 0, and on the wall of the outside of the, and you can see outside of the box the potential energy is infinite. So here, in order to the particle may remain within the box, it is essential to assume that the potential energy on inside the box will be 0 and outside the box will be infinite. So here you can see, as per the Schrödinger wave equation, which we have already discussed. So as per the Schrödinger wave equation, so because there we had seen it for 3 coordinate, but for one dimensional box on one axis, so the Schrödinger wave equation is del square or d square psi upon dx square plus 8 pi square m upon h square into e minus v into psi equal to 0. Here the psi is a wave function as taken as the function of x coordinate only, and you also know at the outside of the box v equal to infinite. Therefore outside the box the equation will be become del square psi upon dx square plus 8 pi square m upon h square into e minus v into psi equal to 0. So just assume this is an equation 1 and another one is equation 2. So after neglecting the e in comparison to infinite, so the equation will become reduced to d square psi upon dx square minus infinite psi. Since one you will multiply this value 8 pi square m upon h square with infinity, so the value will also come the infinity. So in a simplified way we can write this equation d square psi upon dx square equal to infinite psi, or psi you can make an interchange, or you can just rearrange the equation. So psi will be 1 upon infinite into d square psi upon dx square will be equal to 0. So this equation proves that the outside the box psi equal to 0, which implies that the particle can have the restricted inside the box. For the particle within the box, the v equal to 0. So therefore Schrödinger wave equation takes the forms which we can also write in this way: d square psi upon dx square plus 8 pi square m upon h square into e psi. So for the given state of the system, the energy E is constant, which is one of the postulate of the quantum mechanics. So therefore we can put 8 pi square m upon h square into E in a simplest way, can be represented by k square, and this is in a constant. So this terms can be replaced with the k square, and this k is in a constant and it is independent of x. So x means that particular position from where that is the you are finding the probability. So here the equation 4 then will be becomes, it will take another shape. So let's see what is that. So d square psi upon dx square plus k square psi equal to 0. So a general solution for this differential equation is given by, as you know, this equation is generally given by this form: psi equal to a sin kx plus b cos kx. So here you also know a and b are constant. So depending upon the value of a and b, and k and psi can have many values, but all the values are not acceptable. Only those values of uh, y are acceptable if they satisfy the boundary condition, which is psi equal to 0 at x equal to 0 and x equal to a. So there are certain conditions. On the basis of those conditions, only these equation will fit, will be uh, only acceptable condition will be like this way. So now coming to the another here, if you can further simplify, so putting psi equal to 0 when x will be 0. So equation 7 will be becomes, will take the another form: 0 equal to b sin 0 plus b cos 0. So you know sin 0 equal to 0 and cos 0 equal to 1. So the final form, it will take the equation once the x will be 0. So equation 7 becomes will be psi equal to a sin kx. Now putting the value of 0 when x equal to a becomes equation a, this equation 8 becomes, will take another shape: 0 equal to a sin ka or sin k equal to 0. And this equation holds good only when the values of k are integer multiple of pi. Also you can say ka equal to pi or ka equal to n pi, and you know the n is the integer value like these values. So however, like 0 1 2 3, but the value n could be excluded because it makes the overall this value k value will be 0. So for psi equal to 0, for any value of between 0 and a within the box, this is not true because the particle is always assumed to be present within the box. So k can be seen from this equation n pi upon a. So this can take another form of the equation. So this value of the k can be put over on the equation number 8. So you will get this equation will take the another shape like psi equal to a sin n pi upon a into x. So this gives the expression for the eigenfunction y. The expression for eigenvalue of the energy may be obtained by the following equation from, it took from the equation 5. So that equation 5 will took the shape of this. So E will be k square h square upon 8 pi square m. So from here you can calculate the energy. So this is the energy equation. Also you can say this can be helpful to calculate the energy. So substituting the value of k from equation 11, you will get this form: n pi upon e square into h square upon 8 pi square m. So after solving this, after uh, making it in a simpler form, it will take the shape equal to n square h square upon 8m a square. So example 12, you know, equation 12 and 14 are the solution of the Schrodinger wave equation for one-dimensional box. So this is overall, you see the one-dimensional box, you will find the solution in an energy equation which will take the shape n square h square upon 8 m a square. So this is the are the solution for the Schrodinger wave equation for one-dimensional box. So now you see the expression for energy in a particle in one-dimensional box you can represent by this. So here m is the mass of a particle and a is the length of the box. So it is the box length, from 0 to like x, or x is having the value of a. So this is the distance from where you can assume the particle in one direction or in x coordinate. So now there is a certain quantization of energy can be find out from this equation. So how we can see here, we can see since n can have only integral value equal to 1 2 3 etc, therefore equation it follows that the energy associated with the motion of the particle in box uh, can only discrete values, or you can say having the energy which is having the quantized energy. So the integer n is called the quantum number or of the particle. So this is further putting n equal to 1 2 3, you will see the discrete energy level will obtain for the particle of mass m and confined in a box of the length AR, can shown here like this figure. So discrete energy levels of a particle of mass m confined in a box of length A can be seen from this here. If the value of n equal to 1, so then as per the equation, energy equation, that is n square h square upon 8 pi square 8 m a square. So putting the value of n will be 1, so the equation will take the shape of h square upon 8 m a square, and when you will take the value of n equal to 2, so the equation will be 4, it means 2 square h square upon 8 m a square. After solving this, you will see this is 4 h square upon 8 m a square. Similarly 3 you have to put in place of n square, so 3 into 3 will be 9, so 9 h square upon 8 m a square. And similarly once you will put the value of n equal to 4, so this will be 16 h square upon 8 m a square. So it means here you can see by putting the value of n, or you can say the quantum number, then the discrete energy levels can be obtained with the help of for one-dimensional box with the help of Schrodinger wave equation. And similarly, these equations are helpful to see the quantization of energy in case of two-dimensional box and three-dimensional box, which we will discuss later. So here, with the help of Schrodinger wave equation, you can see how it can be helpful to check the discrete energy levels of a particle having mass m and which is confined in a box of a certain length, which is being assumed here like from x equal to 0 to x equal to a. So the minimum value of n could be only 1, because for the ground state energy the n will be the 1. Since n equal to 0 is ruled out, as we discussed during to explanation of the Schrodinger wave equation, so substituting the value, then we will see n square. If you put the number n equal to 1, then obviously this equation will take the shape equal to h square upon 8 m a square. So this is also called 0 point energy. So here the meaning of 0 point energy does not means you have to put the value of 0 equal to in n, in the place of n you should not put the value 0. It means from the ground state the as per the as we discussed in a earlier in a Bohr models. So because that h, if you will put the n value 0, then obviously this whole value will comes 0, so that is not taken. So in a ground state energy or 0 point energy, even once if it is asked to calculate the 0 point energy, then you have to put the value of n equal to 1. So the overall solution will come equal to h square upon 8ma square, and then you will be able to calculate the 0 point energy or ground state energy for a particle in one dimensional box. And if the, like in non-quantization of energy, if you want to, that is you want to calculate for the particles, since if the walls of the box are removed, suppose just assume if the walls of the box are removed, so that the particle is free to move in a field whose potential energy value do not follow any restriction. Because once, if suppose as we discussed earlier here, if the particles restriction is removed, then obviously there is no restriction for this value, so it will not follow as a restricted area. Then the boundary conditions are no longer applicable, because once you had set the boundary conditions like x equal to 0 to x equal to a, and inside the box the potential energy equal to 0. So since you are removing that condition, then obviously the boundary condition ones are you are not applying, so it will be no longer applicable. And so the constant a and b and k can have any value. So the energy of the particle is then given by the equation equal to k square h square upon 8 pi square m. So as the constant k have any value, the energy of the free particle is not can be can be, if it is like a constant, then in this way you can find out the energy uh, for the particle by this equation k square h square upon 8 pi square m. So here the all terms are as usual meanings, mass, Planck's constant, like in case of, if suppose you are talking like h square. So the m, the mass of the, the mass of the particles. So by in, if suppose you are removing this condition non-quantization, or if suppose the non-quantization of energy for the particle you want to calculate, or you want to calculate the energy, so you have to follow up this equation. So apart from all this overall discussion, here the some of the references which you can refer for more details. You can see the online resources like Swayam portal, NPTEL videos, and many more books for the reference. You can refer it out. And now I thanks you all for listening this videos and watching these videos and listening this videos. Thank you so much. Thank you.